Hey everybody, welcome to the shop. I'm Jarrell with Jarrell Education. So today we're going to be going over a problem that's a Newton's law problem, but now the force is going to be varying. It's not going to be a constant force, so we're not just going to be able to add up forces. We're going to have to apply some calculus to this problem. So this problem is, ultimately the one I want to do is where we drop something and as it falls, the wind resistance picks up, so the force is proportional to the velocity. That's going to be the same case with this one, but I actually put it horizontally, and I tried to pick and choose numbers that, made the math as easy as I could make it, but still include all the technicalities that we're going to need, okay? So, all right, let's get into this, and as is always the case, if my content helps you and you like it, please subscribe to the channel, and let me know in the comments if we're doing the right thing, okay? Let's get into this. Okay, let's read through this problem that's different from a typical Newton's law problem. So you got a mass that's shown above is on a frictionless surface and it starts from rest. So I know V sub O is 0. It's being pulled by a 42 Newton force. That's right there. All right, there's an impeding force that's proportional to the velocity of the mass that is given by 3V. Okay, let's talk about this. So I've got this mass, half of a kilogram. It's being pulled forward by a 42 Newton force. Now, if this were time equals 0, when we were just starting, it's starting at rest, so it hasn't moved yet. So that would sort of imply that the impeding force, the backwards force, which is usually something like friction or something like that, is currently 0. So there's nothing to stop it. Then as some time goes on, what's going to happen is, it's going to start moving, because the 42 Newton force will have accelerated it, but now you're going to get a growing force out the back. It's sort of like when you're sitting in a car that's standing still. If you put your hand out the window, you don't feel any air resistance. But as the car moves forward slowly, you'll start to feel a little bit of air resistance. And then when the car goes fast, you're going to feel the air really pushing back on your hand. So it's sort of like that. And this would be like maybe, like at time 1 second. And then at time 2, 3, or 4 seconds, you're ultimately going to get to a place as it speeds up where here's the 42 Newton force, and as it picks up speed, eventually, right, this force is going to end up being equal to the 42 Newton force, and then the thing's not going to speed up anymore. That would be called terminal velocity, okay? So if we just apply Newton's law, so for part A, all right. Now, again, I also want to point out, I'm not really talking about force normal and mg because they're not relevant here. There's no friction. All right. So in the x direction, if I say the summation of all the forces is equal to ma, all right, for this example, that would mean I would have 42 minus 3v, and that would be equal to mass, well, I should just write it in, 1/2 times the acceleration, since 1/2 is the mass. But if I've reached terminal velocity, it's right here. It's this situation where it's sped up enough so now that the backwards impeding force of 3v has equaled 42 and it's not going to speed up anymore. So I can basically say, oh, okay, well, if I'm looking for terminal velocity, I know that's going to be set equal to 0. So I can say 42 minus 3v, and I guess we could say vt for terminal velocity, would be equal to 0. Now, when I solve this, I add 3v to both sides. I get 42 is equal to 3v terminal. And then I divide both sides by 3, and I get v sub terminal is going to be equal to 14. 42 divided by 3 would be 14. Okay, so now we're going to sketch what we think the velocity graph ought to look like for something like this. So what happens in the beginning is we know that the initial velocity is 0. Now what we mean when we say terminal velocity is it's not really going to speed up anymore after that point. So what happens, what I'm thinking of, first of all, we know as time goes on, it's going to get faster. And when this force, when that 3v, as it just starts moving, when it's not that big, like in the beginning, right after time 0, you're going to have the 42. You're going to have the backwards force being pretty small in comparison with the 42. So I would expect this thing would go up, and at first it might look linear, like with a constant acceleration. But then as this force grows, it's going to have the rate of change of the velocity decrease. Now notice the velocity is not going to decrease, just the rate at which is the weird way to say it, the rate at which the velocity is increasing is going to decrease. So then the shape of the curve probably is going to look something like this. and you're going to gradually approach terminal velocity. Okay, so that's what I'm expecting v of t to look like. Now in the next question, we're actually going to find v of t and see how we did. All right, so now for part C, the third part of this problem, we're going to apply Newton's law again, but we're not going to find the terminal velocity. We're not going to find the velocity that's going to ultimately approach. We're going to find the velocity for any given time. So here we go. Summation of all the forces is equal to ma, and again, we're only looking at the horizontal direction. So I would have 42 minus 3v is equal to 1/2 times a. Okay, now up until this point exactly, I don't think there's really any calculus involved. But now we're going to kind of switch over to have some calculus. So look, here's what we have. We have 42 minus 3v is equal to 1/2. And don't forget, a is the derivative of the velocity. So I can write that as dv dt. It's the derivative of velocity with respect to time. All right, so now what I'm going to do, all right, so there's a little bit of calculus, but now I'm going to spend some time doing some algebra, cleaning this up to make it as clean as I can. Now, if you haven't watched the video before this in part 1, go back and do that. Otherwise, some of the things I do here they're not going to make total sense. Okay, so let me scroll up a little bit so I have some room. All right, so let's multiply everything by 2. So I have 84 minus 6v is equal to dv dt. And now I'm going to multiply both sides by dt. So I have this. I have 84 minus 6v, and that's all multiplied by dt. That's going to be equal to dv. All right. Then I'm going to divide both sides. I'm going to divide both sides by 84 minus 6v. And the same thing over here, 84 minus 6v. And then I'm just going to switch the order that I'm writing it around in. So this right here is really going to become 1 over 84 minus 6v dv is equal to, since that's going to cancel out, plain old dt. Okay? Now what I'm going to do, again from the last video, I'm going to doctor this up a little bit to make the integration process a little bit easier. So okay, so let's take this and move it up to here. All right? So now what I have is 1 over, I'm factoring in negative 6 out of the bottom. So inside, that's going to make that negative 14 plus v. Close the parentheses, dv. And then that's going to be equal to the other side, which is just dt. Now I'm going to multiply both sides by negative 6. So what I have now on the left is 1 over v minus 14 dv is equal to negative 6 dt. Again, I just multiplied the left by negative 6, so it canceled out, and then I multiplied the right by negative 6. And so now I'm going to take the integral of both sides. All right. Now, just like I said before, go back and watch part 1. All right, if you haven't seen it already. So on the left, I have the natural log of the absolute value of v minus 14 is going to be equal to negative 6t plus a constant. Okay, now I have to solve this for v, and to do that, I make the left and the right exponents of e, right? So I basically raise e to the both sides power. And what I know now is e to the natural log of undo each other because they're inverses, and I just get v minus 14 is equal to e to the negative 6t plus a constant. Scroll up a little bit. Now that's the same thing as saying v minus 14 is equal to e to the negative 6t times e to the c. And remember, e to the c is its own constant. So now v minus 14 is equal to some number, that's e to the c right there. I'm just calling it a because it's still a constant. I'm just giving it a name, e to the negative 6t. So that would mean that v is equal to a, some constant, e to the negative 6t plus 14. And now my only job left is to figure out what that a value is. Okay? So I have an initial condition, if you recall. I remember that v of 0, the velocity at time 0, it started from rest, was equal to 0. So when the time is 0, the velocity is 0. So I can put in a 0 for v and a 0 for t. And then I'll have this. Scroll up a little bit more. I have 0 is equal to a. Now remember, this is going to be e to the negative 6 times 0, which is just 0, and e to the 0 is 1. So that this whole term is just a plus 14. And then I subtract 14 from both sides, and I know that a is equal to negative 14. Okay? So now here's what I have. My velocity function, when I put a back in. V of t is equal to negative 14 e to the negative 6t plus 14. That's what I have. Okay? So now let's actually look at a graph. I'm gonna fix this up a little bit. So what I'm going to do is I'm just going to factor the 14 out of there. So I have v of t is equal to, I'm going to pull a 14 out, and then I have 1 minus e to the negative 6t. Okay, just so we know, 14 times the 1 gets me that 14, and then 14 times the negative e gets me that term right there. Okay, so one more time, v of t is equal to 14 times 1 minus e to the negative 6t. Now, we already sketched what we thought the graph should look like. We think it should look like this. This is velocity, this is a terminal velocity, and the curve should look like that, where it's asymptotically approaching the terminal velocity. So now I'm actually going to bring up a graph, and we're going to graph what this function looks like. All right, so here you can see, right, I graphed this on some grapher that I have here on my iPad, and each of these blocks right here, you know, this is 2, 4, 6, 8, 10, 12, 14. So I know that's 14, and if you look across, yeah, it's asymptotic to that. And I have the function typed in right here. Okay, that's exactly what we found. So this sort of matches. This should make sense to what would happen, how the velocity would look over time when there's an impeding force that's actually changing. And that's the hard part. That's where the calc comes in. But this is the whole process. So in the next video, I'm going to switch over to doing a problem where I drop it with respect to gravity. And what's nice is it's going to be almost the same exact method. Okay? I just thought it was a little bit easier to start with this and try to make the numbers work out as best I could.